Okay, today what we are going to do, kids, we are going to begin talking about modeling ratios. Yeah, it is going to be really fun. And today we're going to get a little help from a friend of ours, my friend and dog Patterson. Woof, 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 woof. Hi, Patty. How are you, girl? You gonna help us do some math today? Roof, roof. All right, very good. Here we go.
Hey guys, has anybody seen any tuna or garbage cans? I'm kind of hungry.
Rrrr. Patty, you be good to our friend Mr. Raccoon.
Okay, I'm going away, you guys. See ya, looking for something to eat.
Anyways, what we're going to do, kids, is we're going to now go on and talk about modeling ratios. You've already had a chance to hear what the fox had to say about modeling ratios, and now we're going to take a little look at them. Patty, what do you think we need to do to help the kids understand this? Roof, roof. Well, you're right. They did a good job of modeling the video to us, but let's kind of talk about it a little bit more. Okay, kids, let's remember that in this situation, they're talking about the ratio of footballs to soccer balls at a sporting goods store. And it is a 3 to 5 ratio. Okay, so our initial ratio is we have our 5 footballs and we have our 3 soccer balls. So that means, like they said in the video, for every set of 5 footballs, we're going to have 3 footballs. Now, what we're talking about in this situation is some real-life mathematics. Okay? So let's go on and see how they solved this problem. In this problem, they solved it by creating a model. Now you'll notice that, remember, they said that they're going to take the number of footballs, which was 5, and the relationship to soccer balls, which is 3, and it gives you a 5 to 3 ratio. Now here's a model of it. So if you're going to create a model of a ratio, what you would want to do is you would want to draw a tape model. And in that case, you could just make rectangles, okay, to represent the parts of your ratio. You'd want to make them the same size so that they look proportionate to each other, okay? So that's the first thing that you would do. Then you'd want to ask yourself, well, okay, how many total footballs do we have? Because we know that we have 100 footballs, and so our ratio is going to go from 5 to 3 to 100 compared to something else. Well, in this case, we know it's 60, because if we take 100 footballs and we divide 100 by 5, we get 20. Bing! I know that I can put that 20 in each one of these boxes, and that tells us that for all my soccer balls, okay, so I would have my 20 soccer ball, I would have my 20 for my footballs, and then I would add those up, and I would get 60, okay? So you could end up, you'd have 100, and you'd end up with a ratio of 100 to 60. Woof! Woof! You're right, Patty. We could do it mathematically as well. In other words, we could take 5 to 3 and set up equivalent fractions such as this, or equivalent relations. So we know that 5 times 20 would give us 100, and 3 times 20 would give us 60. So even if we didn't know how to make this model right here or here, we could still do it algorithmically. Woof! Yes, algorithmic is a big word and it just means doing the math. Let's take a look at another problem. In this situation, we're learning about a double number line diagram. Okay, and this is the double number line diagram. What do you notice about the information on this? So take a look at it, and then look at the question here. We have Kate can run 2 miles in 23 minutes. That's pretty important. At this rate, so that's a rate, 2 miles every 23 minutes. At this rate, how long will it take her to run 10 miles? Well, what we know then is that Kate can run at a rate of what, Patty? Woof, woof. Yep, she can run at a rate of 2 miles to every 23 minutes. What else do we want to know from this problem, Patty? Woof, woof, woof. Yep, we know that she wants to go a total distance of 10 miles. So the unknown is how many minutes it will take for her to go that 10 miles. Well, we can do it algorithmically, or we can create a double line diagram to explain it. Now let's look at the double line diagram. Notice the parts. We have our ratio, which is 2 to 23, and we've taken our 2, which is our miles or our distance, and we're going to take our time, which is 23, and we're going to make 2 lines across there. So we're starting out with our ratio of 2 to 3. Then we know that we're going to travel or want to travel 10 miles. And what we want to do then is we want to figure out how can we go up in even increments or multiples of 2 until we get to the 10 miles. So we're going to go from 2, 4, 6, 8, 10. And then we're going to come down here, we're going to increase. Now remember, for every 2 miles, it's going to take 23 seconds. So if we go 4 miles, we're going to add, because we're doubling our time, we're going to have to double 23 to become 46. Well, now if we go another 2 miles, we're going to have to take another 23 minutes, and we're going to be up to 69 minutes. If we go another 2 miles, we'll be up to 8 miles, and then we have to add another 23 minutes to 69 minutes, and we get 92. These are all going to be equivalent to the original ratio. And our final amount will go another 2 miles, and that gives us our 10, and that means that we have to add another 23 to 92, and we get 115 minutes. So our new ratio will go from 2 miles in 23 minutes to 10 miles in 115 minutes. Woof, woof. You're right, Patty. We could actually do this mathematically. We could take and we could say, okay, what number can we multiply 2 by to get 10? Well, in this situation, we would multiply 2 times 5, and that would equal 10. So if we multiply this term by 5, we have to multiply this term by 5. So let's see if our math works out. 23, let me do this in my head. If I take 23 and times it by 5, 5 times 3 is 15, 5 times 2 is 10 plus 1 is 11, that gives me just what I need. Very good, very good. Okay, so that's how you use a double line graph, or a double line double number line diagram. Arf! 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 You think they're ready to try one on their own, Patty? Woof! Woof! Okay, well, let's go see if we can't find one for them to do. Oh, here's a good one for us. Why don't we take out a piece of paper right now? We have some blocks set up for us, so we're going to do a tape model here. Let's take out a piece of paper and see if we can't model this situation ourselves to figure out what the ratio, the equivalent ratio will be. So go ahead, kids, I'll pause the video and then you can do the math. Okay, here we go, kids. If you're not done, why don't we look at the example up here and you can follow along. Now it tells us that Ty is making some trail mix based on a recipe that combines 2 cups of nuts with 3 cups of granola. Now these two numbers will form the basis of our ratio, our starting ratio. So our starting ratio will be 2 cups of nuts and 3 cups of granola. And what we then keep, if we read on, we see if Ty has 6 cups of nuts, how many cups of granola should he use? So, well, he has 6 cups of nuts. All right, and he wants to figure out an unknown amount of granola. So how much, in order to use all these nuts in the correct amounts, how much granola will he need to do that? Well, in this situation, what you can do is you can say, well, if I take 6 and I divide 6 in my head by 2, I will get 3. So I can say to myself, for every 2 cups of nuts, I will need 3 cups of the granola, okay? So then I know that I'm going to have to put 3s in here, okay? And then I can say to myself, well, I'm going to have 1, 2, 3 sets of 3, which would equal 9. So I would need, if I have the 6 cups of nuts, I'm going to need 9 cups of granola. And the answer is 9 cups. Maybe what we need to do then is do it mathematically. Some of you even did it in your head, didn't you? So let's look at it from an algorithmic point of view. Let's start out with our original ratio, which is 2 to 3, and we want to go over and create a ratio of 6 to something else. Now remember, you have to keep your units the same on top and bottom, and then we know that 2 times 3 equals 6, so 3 times 3 equals 9. So now we have plenty of both nuts and granola to make a delicious treat. And I could use something delicious because I'm falling apart. I feel like, oh, I fell apart. I could use something nutritious to hold me together. Well, let's try another one now. Roof, roof, roof. Okay, Patty, you can read the problem to the kids. Roof, 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 roof. Yeah, humans do a lot of painting. Roof, 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 roof. Okay, very good. You think the kids should do this one on paper also? Woof! Oh, and you want them to make a double number line to model these equivalent ratios. Well, you heard it, kids. Patty wants you to solve this problem using this type of diagram. So why don't you take out a piece of paper and give it a shot? Woof! I'll pause the video, Pat. You're a silly dog, Pat. Okay, kids, if you're ready, here we go. If not, I'll pause the video again. Woof! Over here, Pat. Let's get out of the way of the math. Okay, let's take a look at what we have. Angela is helping her father paint a fence. She can paint 3 sections of the fence in 25 minutes. That means that 3 sections are going to get done every 25 minutes. That is our original ratio right there. All right? Now, if we make a double line model, what we're going to do is we're going to need a line for the sections, and you're going to need a line for the minutes. Okay? So you'll have a double line, and each of these will become number lines. So we're going to start with 3, and what we want to know is how many minutes will it take for Angela to paint 12 sections of this fence? Well, we want to go from 3 to 12, which means that 12 is actually a multiple of 3, and we can think in our head that we're going to take 12 and we're going to count up from 3, and we'll go 3, 6, 9, 12. Those are all multiples of 3, so we'll need to make a line for 6, because 3 plus 3 is 6, and a line for 9, because 3 plus 9, or 6 plus 9 is 9, and then we're going to move that 12 a little closer to make it look good. And so we are now where we want to be in terms of our 12 sections. Now, our ratio tells us that for 3 sections it takes 25 minutes. Excuse me. So that means for every increase of 3 sections, we have to increase by 25. So we'll have 50 here, increase another 25, get 75, increase here, and we get 100. So that tells us the answer to our problem. If we want to paint 12 sections, it's going to take us 100 minutes. Woof, woof. Okay, we'll check the answer, Pat. And sure enough, it tells us 100 minutes. Very good. Okay, well, I think that's about it, don't you, Pat? Woof, woof. All right, let's head on home now. Oh, ho, it's me, Mr. Fox. Mr. Fox, I'm back. Yes, I am, I'm back. Huh? Hey, where is everybody? I'm all by myself. Oh, it's that dog again. I'm out of here. Oh, I lost my head. Can't do that. I lost my head. Okay, I'm out of here. Bye, dog. Hey, look at that. It's a can of tuna. That's some great tuna. Hey, raccoon. Got some tuna? I could use some tuna. I just ran away from a dog. Got some tuna. Thanks, raccoon. Okay, see ya. Bye. Woo!